Microphone test 1 2 3 1 2 3. Microphone test 1 2 3. Okay. Hello everyone, welcome back to the joy of learning Kotlin. So let us first begin with the problem that we have left yesterday. Is it this one? Almost increasing sequence, yes. And yeah, yesterday we have come up with a solution, but the solution is not efficient enough, so it's failing the last test. Let's see if it's repeating. And later today we're going to talk about one of the really significant, I guess, to me at least, a very important feature of Kotlin, which is null safety. So we're going to talk about that later. First of all, let's first try to finish this problem here. Yeah, so as I mentioned yesterday, the problem here is this is an algorithm which is of O(n) square. It is O(n) square. I am going to give a really basic introduction to what O(n) square is today, but it's not the main purpose of this lesson, so I'm not going to talk a lot about it, but I'm going to talk a little bit basic about it. So what is big O? Big O is a way we analyze an algorithm. So the n square here means that it's the complexity of this algorithm is of big O n square, and it means like let me first give some example of these. Big O1, what is the function that is example of big O1? O1. So if you return whatever directly, this need to be an integer here. If you return anything directly, it's it's big O1, or actually usually we have a parameter here. Let's call it n, and it's of type integer. Then this one because every time it just simply return, no matter how large this n is, no matter the value of n does not make any difference here. So for that example, this one is big O1. And to confuse you more, because big O means it is of the complexity, upper bound complexity. So there are actually three items: O, sigma, and theta. These are all complexity ways that we can describe a complexity, which you can say is the the efficiency of an algorithm. So big O is the upper bound, and sigma is the lower bound, and theta means that it is both upper bound and lower bound. So for example, let me think for a while. To make it more like, make it a little bit more complex, if there is something like for int this is going to be Java because I don't know how to write this in Kotlin, but or maybe I should check it. Let's see, for loop in Kotlin. I think there's a 2, I guess. 2, no. Here, I in 1 to 3. So for this is also something new to me. If you want to do a for loop in Kotlin and you want to iterate from 1 to 3, you can use so this is probably an iterable, some kind of iterable collection class here, because we have learned earlier in yesterday and the day before yesterday that we can use the syntax in an iterable class, and you can iterate through it. So this is probably a shorthand of some iterable class. So if we write it this way, it's, although there is a loop here, the complexity of this algorithm is still big O1 and sigma 1 and theta 1. Why? Because this loop here is not going to influence the complexity in terms of n. The n here is not going to change how many times we're going to loop here. So basically you can define these complexity classes as what about this? If you do 1, 2, 3, 4, 5, 6 times, you would want to like describe it as big O6. Well, this is correct, but it is in big O we don't really care about the constants, so it is also equivalent to big O1, and that would also be true if we have a loop for I n 1 to 3 here. This is still true even if this is a super big number here. It is just simply not, it does not take n into account. The n is not making any difference here. However, if from 1 up to n, if it is like this, so now n comes into play. For this case, we're going to call this complexity of big O n, because it's going to run n times. So this is also true for this kind of examples. If it's again j from n to 1 to n, sorry, this should be n. I'm always confusing this with Java, n. So this is now big O n square. Again, if there are some constant like this is run so many times, it is still 3 times n, but it is still equal to big O n square. Okay, so let's come back to the problem and talk about why is it big O n squared. So there is a loop here, which is related to the length of the sequence. So this loop itself is going to be big O n. And here in each check increasing, because we iterate through the sequence again, and it is related. So it is related to the length of the sequence n. So this itself is big O n again. So because in every operation in these indented by these, I mean the subprocess of this line or this block, it's going to be O n inside. So this is going to be O n times O n, and it is equals to O n squared. So it seems like the answer is not going to accept an O n squared algorithm, so we're going to improve it to somewhere in between. So basically, because we can memorize these checks, these comparisons, so a really intuitive but a little bit complex way to solve is to cache. By cache I mean to memorize what is already computed, because you can see that in these operations we are already calculating a lot duplications. We're in this example, let's take 1, 3, 2, 1 as an example. 1, 3, 2, and 1. We're in each iteration, when skip equals to 0, we're comparing 3, 2, then 2, 1. When skip equals to 1, we're comparing 1, 3, and skip 1. So 1, 2, and 2, 1. When skip equals to 2, we're comparing 1, 3, and 3, 1. And when skip equals to 3, again we're calculating 3, 2, and 2, 1. As you can see, there are a lot of duplicates here. This and this, this and this, and this. Why? Wait. 3 and 2. Oh, this is actually 1 and 3 and 3 and 2. Oh yeah. So look, this is a duplication. This is a duplication, and this is a duplication too. So these two are not duplicating because these are comparing skipped pairs that cross over skipping items. So we can simply memorize these, and it's going to be easier here. This is a way to improve it, but I think this is not going to be the best way. But with these memorization, I think we can drop our calculation from we can improve our performance from O n squared to O n. Let's first start with the comparison. So let's first have a map. I don't know how to have a map in Kotlin. Map, Kotlin. I think we can simply use these old items in Kotlin. Oh, and here's one thing. We haven't talked about how to call constructors in Kotlin yet, so I think it's simply this. just do this one, and the declaration would be cache of value cache of type HashMap equals to HashMap of what's the type? Integer to integer. So anyone who is not familiar with this map type, it's basically a dictionary. So we're going to give an integer and it's going to return us another integer. It works a little bit like a function. There's an input and there's an output. That's how we this is how we use a map. So we can skip this HashMap here because we can see that this is inferred. It is going to be a HashMap, unless we want to do it this way, which usually is a good practice in Java. I'm not sure if it's still a good practice in Kotlin, but yeah, let's point it to map cache, and we need to check the value of the cache. So we're going to pass in the cache and pass in the sequence. And for in each loop, oh wait, I think I know something I can enhance today. Maybe we can simply do this 1 to sequence.indices. Yes? No? 1 to sequence indices -1. I guess this is going to do it. So we don't need this skip now anymore if we can write it this way. This and this is equivalent. I mean this one and this one. So let me check. Oh, is anyone hearing my? Am I still online? Am I still live? Hello. Okay, I think I'm live. So, did anyone leave some message there? No. So feel free to leave a message in the console, so I can respond to you if you have any questions there. So where were we? Oh, we're writing this cal cache, which is where I'm going to do the calculation of the cache and cache it. So I think this one is actually Boolean here. So let's name it is less, larger, smaller than next. So basically I am going to use it this way. If I pass in 0, because item 0 is smaller than 3, so it's going to return true. And for if I pass in 1, because item 1, which is 3, is larger than 2, so we're going to print false. This is the purpose of the cache. So let's do it here. We're going to, in each iteration, we're going to cache dot put. If this one is smaller than next, so what's it? If it is smaller, so this is the first item we will we're going to put the first index into the map and the value of as the key, and the value is going to be if the next one is smaller than, if this one is strictly smaller, so is this correct? Smaller, so I think this one we should remove the equals here. Why did I keep the equal there? Oh, because, okay, smaller. Okay. So it's going to return nothing. So cache. Where's the declaration of cache? Oh, there it is. So let's check for compile error first. Oh, so we need to infer it. That's the first problem. And type expected, so it does not infer directly here. Oh, that's interesting, because in Java this is going to be okay. Function invocation have map. Oh yeah, I'm not. Oh, this is why. So maybe we can just simply do it in this way. We can't call a constructor, so simply plus add the braces. No, it's still expecting. Why? That's interesting. So, again, we're missing the types here. And sequence indice -1 expected type. Sequence.indice. Oh, it's not going to be indice. It's size -1. I hope there is a way that can do it easier. No. Yeah, no invoke here. Put. No put? No, this is not possible. No put? Really? No. On soap reference. No, what is cache.put? Map in Kotlin. Is it not going to have a put? Is this even possible? Oh no, it really does not have a put. So Oh, it needs to be a mutable map. Yeah, I think we need to have it be a mutable map. Mutable map here. Because there are, I'm not sure about this, but it seems like there is, oh, input type is integer, but integer was expected. Oh, so integer and int are different in Kotlin. So it seems like this int here is going to be a wrapped type, I believe. Oh, this is interesting, but we can look at it later. But this is, we can simply fix it with this. Oh, so it probably is a new safety thing. Oh, and it passed? Why? I have not changed. I have not changed. Oh, because this is just test, run test, yeah. So let's push put the map into these check increasing function, and instead of doing the check, doing the comparison, let's simply do the cache. So where is it? Here. If cache second index 2 plus 1, if not, I think that's it. Oh, actually, seems like I am not. Oh, so we do need a check here. Check increasing index to be removed. Where is this? Check. Ah, there it is. Boolean. Why is this a Boolean? Oh. So what is a Boolean, type safe Boolean in Java Kotlin? We plan to talk about no safety, but after this, but we actually run into this Boolean, comparable Boolean. So maybe simply Boolean. I don't know. Is this going to work? Does this even compile? Yeah, it does not compile. Is there a int? Yeah, there is an int. How about a boolean? So yeah, this is simply either true or false. So we can't simply do a boolean here, but since it is not nullable, why would we need to do the type check here? Cache. Well, because we know it's not going to be null here, so we can cast it into a complete route on the nullable real estate. So maybe we're making it confusing. We should maybe do it this way. Or maybe we're not writing not this way in Kotlin. Inversion. Oh, maybe that's true. Inversion in Kotlin. So it's simply not, maybe? Let's try not. This. It's not highlighted. That's weird. Yeah, it's still unresolved. So how do we write not? So negation in Kotlin. Is there a not? Not in, not is. Operators. Assert non-null. Not equal. What about negation? Is there no negation? Logical, yeah. Logical negation. Yeah, there is a not operator, but it seems to get confused with the non-null assertion here. Infer type is boolean, but boolean was expected. Well, why? Why is it a maybe the map is always returning a boolean. So if that's the case, we need to assert that it is non-null here. But boolean was expected still. Why? Infer type is boolean. Oh. So how about casting it to boolean? Although this actually sounds a little bit stupid to me. Let's first Google this. Ah, this is Android. I don't know why, but this is Android. Interesting. Oh, this sounds a little bit stupid here. Right, if we're not going to fix this, we're going to fix it the stupid way I suppose. How it's still not compiling. Classifier boolean does not have a companion object. What's a companion object? Expecting an element. Oh, this is terrible. Kotlin casting boolean to maybe simply do this. As boolean. Is it going to work? Okay, it worked, but I need the negation, so it somewhat worked, but I am actually not making this faster because although I'm caching, but its comparison itself is an O1 complexity, but also a map lookup is also O1, so it is not promised that we're actually running faster here. We could even be running slower. No matter which case it is, we're going to look at this tomorrow because we have reached the 30 minutes limit today. But let's just run it and check if it's going to pass the test. I think no. Yeah, it's still not passing the test. Like I have said, we have made a cache, but with the cache we're still running O(n square. From O(n square to still O(n square. So we're going to come back tomorrow to really fix this. I need to take a deeper look to it. But yeah, I have an answer to I have my previous answer, but I'm not going to leak it now. So I think that's it for today, but I think we can have 1 or 2 minutes to further talk about what concepts we've introduced today. First of all, this is something new. We can use the range, and this is some type of an iterable class. So we can iterate through these items. And secondly, we can let's talk about null safety really fast. The really basics about the null safeties. So in Kotlin, there are nullable types and non-null types. And like for example, string is usually a non-nullable type, and if you add a question mark after it, it becomes nullable. So a nullable class and a null, we cannot directly cast a nullable class to non-nullable class. So this is why here we have a we cast this nullable boolean into a non-nullable boolean, and that's why we wasted some time there. And I think that's it. Oh, we talk about map and mutable map, and mutable. Why is this mutable list? Mutable map. Mutable map and map are interfaces that is only in Kotlin, and HashMap should be mutable because we're going to put some items in it. So if it is not mutable, we probably can only get but not put something into it. And we've talked about a little bit about the complexity of an algorithm today, and I'm not going to go deep into it, but if you're interested, just go Google the algorithm, the big O complexity. I think big O will be enough. The big O wiki page. Sorry, not this one. This is a comic. So this is the big O notation, and there are some math here that you might be depressed, but this is just the concept. There are definitely some materials that you can look into, and with these big O notation keywords. So that's all for today. Bye, guys.